here. There we go. Okay. Then if there's not, we will just kind of continue lecturing here. So if you remember in chapter 3, we sort of left off on talking about sort of changes of state in a sense. We talked about really physical properties and also chemical properties. So where we left off was before this, we talked about physical properties. So physical properties, again, as a reminder, really sort of goes with a physical type change. But physical properties, much like the name sort of implies, it's sort of observations and things that we could see in regards to a substance without having to really change what it is. So, things like color, for example, things like shape or physical sort of properties. Most common physical type properties are like the state of an object. Is it solid? Is it liquid? Is it gas? Um, Melting points, freezing points. And then we sort of tied that in when we were at the end here talking last time about chapter 3 with the idea of a physical change. And the really important part about a physical change is what you start with and what you end up with is still fundamentally the exact same thing. So, a couple examples I think that we talked about. For example, the classic one is like an ice cube, right? If you take an ice cube and you let it melt, it is still technically water because an ice cube is H2O, liquid water is H2O. If you took that liquid water and you heated it up and made steam, steam is still H2O. So those are all physical type changes. There's no fundamental change to water in that case. It remains water all the way through. Also, sort of a key part about sort of physical changes is in a lot of cases, you could kind of recover your original sort of substance by physical means like boiling, freezing, those type of sort of processes. Another example, right, would be something like ice cream. Same sort of idea. Ice cream, sort of like a solid to begin with. If it starts to melt, kind of a liquid mess. But if you throw your ice cream back into, the freezer, you got your solid ice cream back, and it's still melted ice cream is still really ice cream. Solid ice cream is ice cream, so it's still fundamentally really the same thing. So the importance of a physical change is really that idea that what you start with and what you end up with still at the core fundamentally the exact same thing. And that leads us into sort of chemical properties and really chemical changes. So when we talk about sort of chemical properties, we're talking a lot of times about the ability of a substance to either kind of go through a chemical change, which is oftentimes referred to as a chemical reaction, or even the resistance to kind of going through a chemical reaction. But the main difference between sort of a physical change and a chemical change is in a chemical change, what we start with and what we end up with are fundamentally different things. And the important part of that is that you cannot get back your original sort of substances by any type of physical means. So, for example, if we take some hydrogen gas plus some oxygen gas and they come together and make some water. Once we make that water, you could do whatever you like to that water. You could freeze it, you could boil it, you could, whatever you want to do to it. But as we know, and hopefully right, if you make, say, boil some water for pasta or something like that, you definitely don't get the hydrogen gas back or the oxygen gas in that process. You get steam, which is still water, right? So we have fundamentally changed the hydrogen and the oxygen into water, which is united at that point and forms something that is completely different from what we started with. We can't get it back. Rust is, again, another very common example of that. Basically, to make rust, you need some iron, you need a little bit of oxygen, and you need some moisture, basically. And it will come together and make iron 3 oxide, which is basically rust. And the difference is when we started with the iron metal was by itself, the oxygen was by itself. But when it forms this rust here, it is chemically united. So you can't really, if you boil rust, I don't know why you want to do that, but if you boil rust, put some rust in the freezer in case you're bored, I suppose, you're not going to get the iron metal back. You're not going to get the oxygen gas back. It has fundamentally really changed into something that is a new substance, and that's the major difference between, say, a physical change and a chemical change. Could you really get back, say, the hydrogen gas and oxygen gas with water? The answer is yes. You could run something like an electrical current over it, which is sometimes referred to as electrolysis of water, and it will break apart into hydrogen gas and oxygen gas. The difference here, though, is this is also a chemical change. Again, we're starting with water, we're making hydrogen gas and oxygen gas. And again, you will not get back the water sort of naturally or anything like that. So we've fundamentally changed it into something different. So major difference between those two, we're talking about chemical, we're definitely starting with something, ending with something that has fundamentally changed, has new properties, and you really can't get back that original substance in most cases by any type of physical means. Here are just some examples of physical and chemical type changes from the table in your book. Obviously, water boiling. Again, water in the liquid state or the gas state, which is steam, is still water, H2O. Copper and a penny, if it's pure copper, copper and wires, it's all copper, just different. Sugar dissolving, again, we talked about this when we talked about sort of mixtures and stuff like that. Even though the sugar dissolves, it's really not gone, as we talked about. So again, if you had some sugar water and you heated it up, what would happen is the liquid part or the water part would start to evaporate. And if you continuously did that, at some point, what you would be left with is, not sure what kind of red sugar it is, but red sugar here, you'd be left with really the solid leftover after all the water evaporates off. And you would have this sugar, which technically you could let dry out, and, you would have your original, sort of sugar back. You could also collect all that steam that's coming off and cool it back down, and you would actually end up with your liquid water back as well. So again, when we do mixtures, even homogeneous or heterogeneous mixtures like we talked about, they're really just physical sort of changes that occurs, as opposed to over here with our chemical changes. I think we even talked about wood burning. Again, if you burn the wood, it's going to make a whole bunch of new chemicals as it's burning. It's going to become ash. You can't really put it back together. Now, if you chop the wood and don't do anything to it, that's just a physical change, right? You didn't really do anything to change it fundamentally. But once you start obviously heating it, it is going to change sort of chemically as well. So these are just a table for your book as well, again, with some of those characteristics that we talked about. Again, physical properties, really those things that you could observe where it doesn't change what the substance is, as opposed to a chemical change where we really do get that fundamental change that occurs from what we started with. So let's take a look at some of these sort of examples here. If ice melts in the sun, again, ice melting into liquid water, that is a change in state. And again, changes in state are very common physical type processes that occur. Copper is a shiny metal. Again, that's really more observational, right? And physical type of property. Paper can burn. That part right here, the can burn part, is implying that you could set it on fire, basically. And when you do, I'm sure you've seen paper burn. You obviously create a lot of stuff, kind of like the wood in the fireplace is going to go through a chemical type of property in that particular case. Silver, that knife that tarnishes, that actually is a chemical change as well. So basically what that is some silver sulfide. So, the silver and picks up some of the sulfur in the air and all around, and it makes that kind of tarnished look that we kind of see when we have some type of silverware sort of going through that process. A magnet removes iron particles from a mixture. That's more of a physical separation, kind of like what we talked about with filtration, which is a nice physical separation process that you could do. Obviously, if you had some sand in there and you had a bunch of metal pieces kind of in it, you obviously could hover the magnet over it. It's going to be attracted to the magnet, the metal pieces. And at that point, if this was a case of sand and metal pieces, you would have all the metal pieces separated from the sand. Metal pieces are still the metal pieces. Nothing's going to change with those guys. Obviously, when you remove the metal pieces from the sand, you're left with just like the sand that you originally started with. And that would be more of a physical type of change. Any questions on any of those there? Talking about these here, are these changes physical or chemical? So burning a candle is a chemical change, although the wax does melt and you technically still have wax, but there's some chemicals in there as well as it is burning and going through that change. We have ice that's melting on the street. Again, ice melting is going really from solid back to liquid. So that again is a change of state, which means it's going to be a physical type changing. Toasting that marshmallow there will be chemical, is the fire and obviously some of the properties that are on the marshmallow burning. It's going to go through a chemical change. By the way, when we eat it, also go through a chemical change. If we cut the pizza, that is a physical change. Again, if you have a pizza and maybe you're a square pizza person, if you cut it in squares, still pizza. Sounds good right about now. If you have a circle pizza and you cut it in wedges, also obviously still a pizza. So, it doesn't matter how you cut it. It's still fundamentally a pizza at that point. Nothing's really changed. And as I mentioned earlier, rust is really a chemical sort of change that's occurring. Again, before we do anything, the iron is sort of separated by itself. The oxygen is kind of floating around freely. But when we do form rust, they do sort of chemically unite, which basically means that some type of chemical reaction sort of has taken place between those two. And that would definitely imply a chemical change occurring. Any questions on physical changes, chemical changes, how to tell the difference between them? Again, we also talked about earlier on, I think in this chapter as well, mixtures, homogeneous mixtures, right, is when we mix things together and it does mix and it looks the same throughout. Heterogeneous mixtures is when we put two or more substances together and we see different layers, so it doesn't really mix very well. But a reminder that as we talked about, when we talk about mixtures, even though it may appear a lot of times like in a homogeneous mixture that something has sort of disappeared, it's changed. When we dissolve something like salt or sugar, as we just talked about, it is really still there, even though we can't see it. And we can get it back like through those processes we talked about, filtration or distillation, and we could get them back to their original forms. Any questions on any of that stuff there before we move on to sort of the next topic here? Okay. So the next topic we're going to talk about really is temperature and temperature scales. And as we might have touched upon earlier as well, there really is three sort of temperature scales that we commonly come across. That is degrees Celsius, that is degrees Fahrenheit, and that is Kelvin, which is capital K. Out of all those guys, pretty much in chemistry, if we're dealing with temperature, it usually does need to be in Kelvin. And most of the time in chemistry, we're oftentimes given a temperature in Celsius, and we need to oftentimes do that conversion where we kind of convert it from Celsius to Kelvin. probably outside of this chapter, you're probably not going to do a heck of a lot probably with Fahrenheit. We don't do a ton of it, but obviously that is, as we can see here in the picture, usually what we do take our temperature with, right? And the sort of Fahrenheit scale and stuff like that. But most of the time in chemistry, Celsius is a very common unit that's given in terms of temperature. But most of the time after that, you usually have to convert it to Kelvin. So Kelvin is sort of a pretty big unit in terms of temperature in chemistry. Now, a little difference as well is when we talk about Celsius, it is degrees Celsius. When we do Fahrenheit, it also is degrees Fahrenheit. There is no degrees here. I guess I shouldn't make a circle looking thing, make a box. No degrees that's written here. So it is just Kelvin. So if you had something like 373, you would say 373 Kelvin. You would not say 373 degrees Kelvin. Now, when we talk about temperature, it really is a measure of sort of how hot or cold an object is compared to another. Sometimes people confuse temperature with what is referred to as thermal energy. And there is a difference, but temperature is sort of a measure of, really, as it says, how hot or cold something is. And when we talk about heat, our energy, heat really does go from hot to cold. And what I mean by that is, whatever the hotter item is, it typically will transfer its heat and energy to the colder item. And the colder item will sort of increase temperature. The warmer item will decrease temperature. And if you happen to maybe have both of those things in like a nice insulated container, whatever this guy's temperature is, wherever this guy's temperature is, if this was the hotter one, heat would transfer from the right-hand side to the left-hand side. Again, the right-hand side would get cooler. The temperature on the left-hand side would increase, and they would probably meet somewhere halfway between, both of those temperatures when it's all said and done. We usually obviously use a thermometer to measure temperature, and the thermometer, like any other device, you always want to make sure you look at the scale. For the most part, the scale sort of looks like this. Again, if we look at sort of the dashes between 10 and 20, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dashes, which means each dash is 1 degree Celsius. That would be 11, 12, 13, all the way up. And usually in most cases, again, not 100% of the time, which is why you should always look if you're using a thermometer, but usually in terms of how far you could take that reading is usually to like the first decimal place, usually when you do it on most thermometers that you see in sort of a chemistry laboratory. So how do we sort of go between these different temperature scales? Well, we use really the difference between the freezing point and the boiling point on each of these scales. So on the Fahrenheit scale, we are freezing water at 32 degrees Fahrenheit, and 212 degrees Fahrenheit is where we're boiling water. That's about, as it says there, 180-degree sort of separation between where it freezes water and where it boils. And that's a little bit different than on the Celsius, 0 degrees Celsius where we freeze, 100 degrees Celsius where water freezes. That difference there, as you can see, is a 100-degree difference. While on the Kelvin scale, 273 is where we freeze and 373 is where we boil. And that also is a 100-degree difference between them. That 100-degree difference and also that 180-degree difference between the freezing point and the boiling point is ultimately how we kind of convert between these different scales. So let's talk about first the Fahrenheit and the Celsius scale. And that sort of difference between boiling and freezing comes out to be a factor sometimes referred to as like 1.8. And if we have the temperature in Fahrenheit, we would take 1.8 times the temperature in Celsius, and we would actually add a 32 to that. And that would give us the temperature in Fahrenheit. We could also rearrange this equation, and the temperature in Celsius would be the temperature in Fahrenheit minus 32 divided by 1.8. Again, the 1.8 is the same number that you might have learned, which is 9 over 5. So if you divide 9 over 5, you get 1.8. Sometimes you might even see it 1.80 as sort of that number. And we'll talk about really, because there's this sort of difference or different ways you could kind of calculate, this sort of calculation, especially that 1.8 part. It does actually affect things like, kind of significant figures and sort of how we deal with that in terms of temperature. So the temperature conversions you do need to know. So obviously those guys box right there, those two equations, again, is something that you do need to know. So just to talk about the stuff we just saw on those scales, the temperature at which water freezes, that's going to be 0 degrees Celsius. 0 Kelvin is not correct, or 0 Fahrenheit is not correct. In terms of boiling water, we're going to look at 373 Kelvin. 32 is freezing there, I believe, for water, and 100 is not boiling for water on the Fahrenheit scale. That's 212 there on the Fahrenheit scale. How many Celsius difference between freezing and boiling? In Celsius, it is that 100-degree difference. 180 is the Fahrenheit scale, and 100 is also the Kelvin scale in terms of the differences between them. Any questions on that? So as I sort of jumped the gun there a little bit and wrote the equations, again, this is our equation to go from Celsius to Fahrenheit. And again, doing that rearranging to go from Fahrenheit to Celsius. So as I sort of alluded a little bit earlier in terms of significant figures, let's actually talk about sort of the general rule that people follow when you're strictly doing a temperature conversion. So what I mean by that is you're not really doing much with the number other than taking it from one temperature scale to another. So you're just going to simply do just a straightforward, excuse me, you're just going to do a straightforward temperature to temperature conversion. So the 1.8 is really like the conversion factor that allows the 1.8 really where it comes from is really the difference between where water freezes and boils. And that's really that difference that we see, that 180-degree difference. So if you remember on that chart, we saw a 180-degree difference between freezing and boiling on Fahrenheit. It's a 100-degree difference between Celsius freezing and boiling. When you divide those two, that's actually where the 1.8 actually comes from. So it's sort of that conversion factor that allows you to go from Fahrenheit to Celsius. It also is, again, some people when they're younger learn instead of 1.8, like the fraction 9 divided by 5, that also is 1.8. So, that's sort of where that comes from. It's really the difference between freezing and boiling points on the different scales. You're welcome. So it actually does relate in terms of significant figures, what I just mentioned, because there is sort of some variance, if you will, in terms of what people sometimes will use for that number. So as I mentioned before, some people will use 1.80, some people will use 1.8, some people will use that fraction there. There's a lot of difference in terms of what you could get in terms of significant figures if you decided I want to just be very rigid and stick strictly to significant figures. In addition, this 32 as well has some differences there. So to sort of get around that, when we're just doing a simple temperature conversion from one temperature scale to the next, what we want to do in terms of significant figures and temperature conversions is basically the answer should look like the original number. And again, this is really specific for just doing temperature conversions. So what do I necessarily maybe mean by that? Well, if I take 32.5 degrees Celsius and I want to know what is it in degrees Fahrenheit, I would put this into my formula. The temperature in Fahrenheit would be 1.8 times 32.5, which is my temperature in Celsius, plus a 32. And when I punch that into my calculator, I end up with 90.5 degrees Fahrenheit. Now, it happened to come out okay in this particular example because my original number went to 1 decimal place. So what I would want to do on my converted number is to make sure I did take it to 1 decimal place as well. So what you want to do is make the original number and the converted number for temperature look the same. So if it was like a whole number, if you had like a whole number and you were converting it into another temperature scale, what you would do is then take it to a whole number. So for example, if I had 102 degrees Celsius and I want to go to degrees Fahrenheit, if I pop it in there, we get 1.8 times 102 plus a 32. On my calculator, I believe we end up with 215.6 degrees Fahrenheit. Now, in this particular case, my original temperature value went to a whole number, which means when I did my conversion, I would actually want to end here at the whole number. And because of that 6, I would want to round up, and I actually would want to report as 216 degrees Fahrenheit. Again, whole number to start with. We made our converted number look exactly the same. And that is the general rule that pretty much everybody follows when they're doing temperature conversions. Again, if they took it to 2 decimal places and you're doing that conversion, when you convert the temperature, you would also take it to 2 decimal places. Any questions on that? Obviously, if it went to 1 decimal place, like the first example, to 1, and obviously like a whole number here, we would round to a whole number. So again, what we're talking about here is really specific for just a straight temperature to temperature conversion. And it's really because, there is a lot of sort of variance that you could have depending on sort of what you choose for the numbers there, the 1.8, the 9/5 and stuff like that. Any questions on that particular one there? So here we have 21 degrees Celsius, and we want to convert it to Fahrenheit. So we do use our formula here. So we would put it in just like we were doing on our other ones there, 21 plus a 32. Again, on your calculator, when you punch that in, you're going to get 69.8 degrees Fahrenheit. What we would want to do based on what we just been talking about is look at our original number, and our original number basically is a whole number, no decimal, which means again, we would want to do some rounding here. We would want to round this guy up to 70, maybe put a decimal there, degrees Fahrenheit. And again, make it look like our original number. Any questions on that one there? Okay. So that is essentially how you convert between Fahrenheit and Celsius. And again, I'll be honest with you, probably outside this chapter, might not see a lot of Fahrenheit happening. Definitely will see a lot of Celsius. And what you'll typically see as I mentioned earlier in chemistry, is you'll oftentimes be given temperatures in Celsius, and for formulas, almost every single chemistry formula that involves temperature usually involves it needing it to be in Kelvin. So this conversion going from Celsius to Kelvin is definitely one that you use a ton. So you use it a lot when you do it. Scientists have learned that basically the coldest temperature possible is minus 273 degrees Celsius. That is what is sometimes called absolute zero. This used to be called the absolute temperature scale, later renamed for our good friend Kelvin, and that is represented by 0 Kelvin. So to convert from Celsius to Kelvin, which is something that you do a lot, the temperature in Kelvin is the temperature in Celsius plus a 273. So that is definitely something you should know, because I could pretty much bet you will be using that conversion, a lot as we go throughout the semester here, and especially if you take chemistry classes. Not used probably as much is going from Kelvin back to Celsius, but in case you need to do that, the temperature in Celsius would be the temperature in Kelvin minus 273. Now, that 273 number really does come from the coldest temperature possibly that's able to be achieved. And the true number is actually not 273. It's actually 273.15. So you'll sometimes see this number kind of used for Kelvin conversion. I would say probably 99% of the people get rid of the 0.15 and just do the 273. Personally, I do the 273 all the time. If you want to keep the 0.15 part, I guess you could. But what happens is a lot of times it gets rounded off anyways. But don't be surprised if you do see somewhere somebody writes this number as, hey, that plus the temperature in Celsius equals Kelvin. Because truthfully, that really is the right number, because this guy right here is actually 0.15 is really the right number here. But very, very super common. People really don't use that 0.15 part of that number. So again, these are two really important sort of temperature conversions. And out of all these sort of temperature conversions going forward and in future chemistry endeavors here in this class, this one here going from Celsius to Kelvin is something that we use a lot. Now, if you started at Fahrenheit and did want to end up at Kelvin, the process would be you would go from Fahrenheit to degrees Celsius, and from degrees Celsius to Kelvin is sort of the process of how you would kind of go from one to the next. So, there's not usually a direct conversion, if you will, to leapfrog it there that most people use. So they kind of do it in a sort of stepwise fashion. All right. So let's take a look here. We have normal body temperatures is 37 Kelvin, and we're looking to, 37 degrees Celsius. What is it in Kelvin? So again, a very common conversion. We would go to our temperature in Kelvin is our temperature in Celsius plus our 273. So that's going to give us 37 plus 273. That will give us 310 Kelvin. And it looks like that would be B in this particular case. And if we wanted Fahrenheit, for example, temperature in Fahrenheit would be 1.8. It didn't ask for this, but just to make sure, if we did it into Fahrenheit, we would take 1.8 times our 37 plus our 32. Again, if you put this into your calculator, you're going to end up with 98.6 degrees Fahrenheit. Looking at our original number here of 37, which is a whole number, we then would want to round that there to 99 degrees Fahrenheit. Any questions on any of those conversions? Okay, so why don't you give one a go here? Let's do minus 15 degrees Fahrenheit. What is it in Celsius? And while you're at it, why don't you do Kelvin as well? So take a minute or so and see what you come up with. What is temperature in degrees Celsius? So why not start with that one? So remember that the temperature in Fahrenheit is 1.8, temperature in Celsius plus a 32. In this case, we are given Fahrenheit, so we do need to rearrange this, and that would give us at the temperature in Fahrenheit, subtracting the 32 to the other side, and also dividing by the 1.8 would give us the temperature in Celsius in this case. And if we put those numbers in, our temperature in Fahrenheit would be minus 15. Again, the minus is important here. Minus a 32 divided by 1.8. Again, if you get the answer on your calculator, it's going to spit out to you minus 26, maybe 0.111, a whole bunch of ones, degrees Celsius at this point. In this particular case, we would be looking at our original number here, and our original number is a whole number, which means we would want to come back here and really round it to this spot. Since the next guy is a 1, we pretty much could just drop the rest of it. And again, we do want to leave the negative though, so that would be negative 26 degrees Celsius, if I make that a C. And that does look like the original question, number letter D there, would be the correct one in that particular case. Looks like we're doing all right on there. That's good. So Kelvin in this case, again, we would have our temperature in Celsius plus a 273. Again, the negative here is important. So negative 26 plus a 273. We're basically subtracting in this case, and we should end up, I believe, with 247 Kelvin. Again, no degrees sign on that. Also, whole number, and we do end up with, I believe, that number right there. Any questions on that particular one? Okay, so again, important to know how to do these conversions. The temperature conversion formulas will not be provided for you, so you do need to know, again, how to do all those conversions between the different scales. And like I mentioned before, maybe outside of this chapter, probably most of the time we are going to be seeing that Celsius to Kelvin sort of conversion. Here again, just some comparisons of the different temperature scales from your book. And again, a couple of things about sort of temperature variations, obviously, in the body. If a body temperature is above 41 degrees Celsius, that is what's considered hyperthermia. Hyper means basically you're going higher there than normal range. Normal range is right about there. And obviously hyper would put you up in this range. That does not look so good. Hyper, by the way, does mean more than. So typically when you do see that word hyper as the first part of something, it's usually referring to more than something. So obviously in this case, if we're hyperthermia, we are higher in temperature than normal. And that would also mean a term that we oftentimes also hear, which is hypothermia, if you're out in the cold, perhaps. And that is going the opposite way. Again, our normal range over here, hypo out in this range. And again, hypo basically means less than. So that's less than normal body temperature is basically what that means. So those two sort of beginning parts of words are very sort of telling in terms of what you're talking about. Again, hyper usually refers to something being more than something, and hypo usually means something that is less than something. And a good way to remember that is that, obviously. So why don't we kind of finish up here with one last example. We have 34.8 degrees Celsius. What is it on Fahrenheit? And why don't we also add Kelvin to this to finish this out for tonight? Okay, so let's take a look here. So again, we have Celsius going to Fahrenheit. So as we've seen a couple of times already at this point, we're going to go temperature in Fahrenheit 1.8, our temperature in Celsius plus a 32. That's going to give us 1.8 times 34.8 plus a 32. In this case, on your calculator, I believe it will spit out you 94.64 degrees Fahrenheit. And again, remember that we're going to follow our sort of general rule here. When we look at our original temperature value, it did go to 1 decimal place. So we would want to kind of clean this up to 1 decimal place. So we would be probably reporting 94.6 degrees Fahrenheit as the correct one. Again, 1 decimal place, 1 decimal place, just like the original number. We also could convert ourselves into Kelvin here by adding our number 273. Again, remember the number is 273, not all kinds of weird other numbers that people always like to try to use. If we do that, we got 307.8. Again, no degree sign on that, capital K for Kelvin. And in this particular case, we're good because 1 decimal place, again, matching that 1 decimal place that we started with, and that would be our Kelvin. Any questions on any temperature conversions, how to do them, the significant figures? Again, what we're talking about here, a reminder in terms of significant figures, is really specific this rule for strictly temperature to temperature conversion. Any questions on anything we just talked about tonight? Okay, so this is actually where I stopped with Monday's class. So our Monday's discussion. So you guys are exactly in the same spot. What that does leave us, though, is a little section of chapter 3 still to go. So like I said before to everybody, in the next couple of days, I'll probably post up a recorded lecture on that little section of it to sort of finish out chapter 3. On Monday, we will continue through chapter 4. And like I said, during lecture as well, again, the exam will be moved, obviously, not next Wednesday, but the following Wednesday, which I believe is the 10th. And we'll cover through chapter 4, and the homework assignments when I get an opportunity the next day or so will also obviously be extended to that date when they will be due officially. Any questions on anything going on or we talked about today? Okay, if you are good, then I am good. Have a very nice weekend. Thank you for listening. If you happen to still have questions on something, I'll be more than happy to hang out and answer them for you. Otherwise, it's the weekend time, right? So have a nice